So welcome everyone to the brown bag session of today, which is called Defeating EDRs Using the Invoke. I'll be your guest speaker of today, and for those of you that don't know me yet, so my name is Jean-François Maes. I've been with NVISO since about 2019, early 2019. Before that, I was a system engineer at a government institution here in Belgium. And now I'm primarily focused on red teaming and also the malware creation of our red teams. I'm also the creator of redteamer.tips, which is a blog that I own and that I regularly post some helpful tips and blog posts for red teamers. Also, since this month, I'm the host of the Voices of InfoSec podcast as well, which we launched. This is a podcast that is tailored for new joiners in the InfoSec community to help motivate them to join, or if they just joined, to actually level up their careers. Other than that, I'm also a SANS instructor for the Sec 699, which is a purple team course. And I'm also a very big believer in Red Team Fit, and I'm a devourer of chicken and other proteins. It's a bit unfortunate that during lockdown, there's no gyms available to me right now. I don't have the space like Dave Kennedy for a home gym, so I'm a bit locked up on that part. But yeah, we just have to roll with what we have, I guess. So without further ado, let's talk about our agenda for today. First of all, I will take you to a short trip down memory lane about how pen testing, and more specifically red teaming, evolved throughout the years, even before I started doing red teams, until the more advanced red teaming that we see today. Then I will talk about the Win32 API, because in order to understand the more technical parts of this talk, which is, well, let's be honest, almost the entirety of this talk, you'll have to understand the Win32 API a bit first. Then I'm going to talk about EDRs and if they are actually malware or not. We will also create our own demo EDR, and then we will see how to bypass it using creation flags as a first bypass. And then we will see the Invoke, which is kind of the point of today to highlight the Invoke and why I love it so much. Then the manual mapping functionality of the Invoke. And finally, we will end with Syscalls. So let's take you back to the earlier days of pen testing. Well, when I say pen testing in the subject or the scope of this talk, I'm actually more talking about infrastructure pen testing and red teaming. So back in the earlier days, before I was a red teamer myself, it was pretty common that you could just be a quote unquote script kiddie and get away with it, because the antivirus solutions back then weren't, of course, the antivirus solutions that we know right now. So it was fairly easy to just launch a Metasploit meterpreter on any box without having to fear a bit of the antivirus. There wasn't so much that you had to do in order to evade antivirus. Most of the things just worked out of the box. But obviously, defenses became better, and our malware or our red team capabilities had to adapt as well, which is what we see nowadays. With the rise and fall a bit of PowerShell tooling and OMSI. So OMSI is definitely out there, and if your EDR or antivirus provider is not leveraging OMSI, I would strongly suggest that you rethink your EDR or antivirus provider, because OMSI is vendor agnostic. It's something that Microsoft launched quite a few years ago, and it's a free implementation basically. So any antivirus vendor or EDR is free to just use it if they want to or not. Thankfully, most of the well-known EDRs and antivirus providers leverage OMSI, but OMSI is obviously not without its flaws. There are very common bypasses available, especially now during the OMSI.fail era that Flangvik launched, which just generates an OMSI bypass by the press of a single button. So it's still quite, well, it's not trivial. It takes you a bit of time and you need a bit of knowledge to bypass OMSI, but it's definitely not something that is impossible to do. So let's talk about the more mature red teams, the more mature organizations, and what like threat actors use nowadays. So you see now more and more that the defenses are getting better, which is definitely a good thing, right? You have things like AppLocker, Exploit Guard, attack surface reduction, and then you have your EDR vendors that are building on top of that, which are quite capable of detecting, well, out-of-the-box payloads. Like, don't even dream of getting just an off-the-shelf Metasploit meter-breather shell on a box with EDR enabled. You will have to do heavy modification in order to get that to work. And even some EDRs have the capabilities to see that AMSI is being tampered with and will alert accordingly. So even if you would disable AMSI, you would still not be able to actually leverage your malicious payload. And the reason why is actually, well, before I dive into why exactly that is, I want to talk about the Win32 API first, because this is a bit where it gets interesting. So the Win32 API, or the Windows operating API, is basically an API that Microsoft uses, and it's open sourced. Well, it's not open source, but the documentation is publicly available to everyone because it allows you to interact with the Windows operating system from an application point of view and from a kernel point of view. So these are the APIs that are out there and that you can use to interact with the system. And it goes without saying that malware needs to interact with this Win32 API at some level, at some point. Otherwise, it wouldn't be able to launch a reverse shell or anything like that. So how it works from a quite high level point of view is you have your Win32 API libraries, or DLLs, such as kernel32.dll. And it's basically a precedence order. So it goes from high level to low level. But on the lowest level is actually the ntdll.dll, and that is what bridges the user mode and kernel mode together. So you have your Windows operating system, you have the kernel that is running your Windows operating system, and then of course you have user land, which is everything that is happening above the kernel, so it's interacting with the kernel. And on that level, so the bridge between user land and kernel land are all the NT functions, and that's what ntdll.dll does. So all the higher level APIs, such as kernel32, will at some point call ntdll.dll to actually bridge the gap between user land and kernel land, so it launches the specific API call that you want to launch. And you will see how that works when we talk about the API monitor in, I think, 2 slides. But let's see first how malware would use this as a practical example. So here, this is a classic DLL injection. So what happens is a threat group or a malware operator, a red team operator, writes a malicious DLL onto disk and then uses a series of API calls to actually inject his or hers malicious DLL into a new process or into an existing process that is already well, open on the system. So some of the commonly used API calls that leverages the capabilities to actually do this DLL injection or virtual alloc. This will allocate memory, virtual protect, which will change the memory protections of the new allocated memory, then the write process memory, which will then inject your DLL into the process memory, and then create remote thread, which will point to the memory space that you created with the malicious code. So that will create a remote thread and execute the code that you just injected to. These are all kernel32 APIs. And if you would look on how that looks like, as a rule of thumb, it's always the best thing to do to actually stay as low as possible. This is true for both red and blue, because if you detect on ntdll calls, then you will by default also capture all the higher level calls, because at one point or the other, the lower level ntdll call will be called. And a nice read from one of my heroes, Rastamaus, is on the slide there as well. He explains how to leverage the Invoke with Syscalls as well, and this is kind of the end topic, the end game of this presentation. as well. So if you want additional documentation, that's a very nice read. So as I already mentioned, at one point or at the other, kernel 32 will call the ntdll, and I will show that first here. So there is a program called API Monitor, and with API Monitor, you are basically capable of inspecting a process and checking what API calls are being made. So what you can see here is an example of a basic loader, which I will execute soon as well as part of a demo. And that basic loader has different kernel 32 calls. So for example, virtual alloc x, write process memory and create remote thread. And as you can see in this slide, on the call tree, you see that virtual alloc x, for example, has an underlying call dependency in its call tree to nt allocate virtual memory. And the nt is important here because all the exported functions of ntdll.tll start with nt. So this is an indicator that your kernel 32 API call is indeed calling the ntdll.tll. So in terms of detection, it's always best to have rules that check for the underlying NT calls instead of using the kernel 32 DLL exported functions as hooks, for example. So this is an example of the basic loader, and if we look at the code of the basic loader here, you can see that I made it quite easy to understand for everyone because I split it up the imports, the structures, and the actual code. For those of you that didn't join at the beginning of the presentation, there's actually a link to the GitHub repository with the code.
It seems like we've lost connection with Jean for a moment there. Let me see what's going on.
Am I back?
Exactly. Yes, you are back again. Okay.
So where did you lose me?
We only missed like 30 seconds or so. So just.
Okay, so to reiterate a bit, if you didn't join the call before I started talking, there's actually a link to the GitHub repository where you can see the source code as well. So if this isn't clear on your screen because your screen is too small or for any reason whatsoever, the entire code is on GitHub as well, so you can follow along there as well. So as I already mentioned here in the imports class, you can clearly see that I'm importing from kernel 32.tll, and you can see it's create process A, virtual alloc x, write process memory, and create remote threads that are being imported into my code and then being actively leveraged here. As you can see, the imports are being called to create the corresponding API calls to actually inject the code. So if we would launch my example loader, what it basically does is I hard-coded a message box payload in there that just says eval payload with breaks as well, so keyboard breaks to actually break between each Win32 API call. And the reason why I did that is because when we come to the examples of my custom EDR, you will see that I'm hooking these functions and that it's going to correspond with an appropriate action every time this API is being called. So as you can see here, allocating memory, writing memory, creating a thread, and that will launch the shellcode, which will be this eval payload message box, which I am going to show you right now, actually. So I hope this is big enough for everyone. I will now paste in my command, which is the demo with Notepad, which will be our process that we spawn, where we will inject the shellcode to. So if I do that, you will see Notepad popping up. Should be noted, obviously, this is just a demo, so Notepad is popping up here with its window attached to it, but it's trivial to just pop up a Notepad without actually showing the window as well. So once this is done, I hit my key to allocate memory, I hit my key again to write memory, I hit my key once more to launch the shellcode, and what do you know? evil payload is now popped on my screen here, so the payload was successfully executed. If I now press OK, it will actually close out my notepad process as well, because in my Metasploit Venom, my MSF Venom, I didn't specify an exit function. So that means if I kill the shellcode, it will kill the entire process as well. So that was the first demo, just to show you how that looks like, the demo of the basic loader. So the bridge from user to kernel land, as I already mentioned, ntdll is a key here. And ntdll is actually nothing more than just a wrapper for Syscalls. And it always has a bit of the same skeleton assembly, which is shown here as well on the slide. So what I did here was I just attached a Windows debugger to an arbitrary process, because all processes actually load ntdll.tll into their virtual address space, because every process needs that. And then I just unassembled one of the exported functions to show you how it looks like. So here you can clearly see the move instruction from R10 to RCX, and the push of a syscall number into the EIX registry. This is something that is being done for every NT function. So every NT function will have this skeleton code, so to speak. The only difference is, of course, the syscall number itself. So in this case, NT allocate virtual memory has the syscall number of 18H, which is 18 hex. And this varies depending on the architecture of your operating system. So it's not because the syscall here is 18H for NT allocate virtual memory on a Windows 10 system, that 18H will also be the NT allocate virtual memory syscall number on a Windows XP, for example. So that varies from operating system to operating system, which is something important to mention here as well. So then I want to talk a bit about EDRs and whether or not they are malware. For most of you that are new here, you have never heard me say this, but for the people that have heard hear me speak before, I've said this multiple times, and it's one of my favorite quotes. In my opinion, EDRs are definitely malware. Why? Well, because they are actually leveraging the same API calls as a malware would do to inject their DLL into any process. So as you can see here on this slide, when I open up PowerShell on a box that has a McAfee endpoint protection enabled, and just looking at the imported modules in Process Hacker, you will see that, for example, ATP amsiguard.dll gets injected into my PowerShell process, which is a DLL of McAfee. So they are also leveraging exactly the same API calls like malware would do in order to load their DLLs into processes. Obviously, the EDRs are using kernel drivers, so it's not exactly the same as malware, but the gist of it remains the same nonetheless. So how do EDRs work now, and why is AMSI, well, disabling AMSI not enough? And this is where it gets interesting, because this is where userland hooks come into play. So here is exactly the same function as I showed you before. So this is an unassembled ntdll ntallocate virtual memory call, which you can clearly see is using the skeleton code of a regular NT call. And here you can see the ntdll unassembled of exactly the same call. So again, the NT allocate virtual memory call, but in this case, it's actually being hooked by an EDR. And you can clearly see, if you compare these two unassembled functions, that there's something fishy going on here, because it's not moving R10 to RCX as a first instruction. No, it's actually jumping to another memory location, and if we would follow that memory location, we would end up into the DLL of the EDR provider, which in this case is my demo EDR that I will showcase in just a bit. So trivia, I already mentioned it though, and because, well, this is not a very interactive chat because there is a delay, I'm just going to give you the answer. But what would happen if you create a loader that calls ntdll.dll functions when your EDR is actually hooking kernel32.dll? Well, it's trivial. Your hooks won't have any use because you're actually calling the ntdll functions directly, which would bypass your hook because you're actually hooking a level on top of that. So that would bypass in EDR, would an EDR only hook kernel32.dll calls, which fortunately is not the case anymore. It used to be more done in like the early days of EDRs. The EDR providers also just hooked the higher level calls, but now that more and more people are leveraging the ntdll calls directly, the hooks are now placed on ntdll, which is a very good thing, of course. So to make it even more obvious, imagine even if you have an EDR that is hooking on ntdll.dll on all the exported functions there. Well, what happens if you know how the ntdll call works, and if you implement a new function that is just doing exactly the same as the ntdll call? So imagine that I know how nt-write process memory is implemented, and I create a new function. I call it my function, and I just copy paste the entire implementation of that code into my new function name. What would happen then? Well, what would happen then is your EDR will not catch it because it's not hooking that function. It is only hooking the exported functions of ntdll.dll, which is quite interesting because that's exactly what we will do in our Syscalls as well. When we implement direct Syscalls, we will take the function prototype of an NT function, which is assembly, and we will just write the assembly once again and create a delegate to that and point our code to that new delegate. So it will use our code, which is the exact same implementation as the ntdll code. So it will react exactly the same and behave exactly the same, with the addition that the added benefit that your EDR is not hooking on that function because you just wrote it yourself. So the EDR is not hooking on that. So thanks to Ethical Chaos, he actually wrote a nice blog post about it. He created his own EDR and also showcased how to bypass it. I realized that this slide is probably way too small, so you will have you will need binoculars to actually read this slide. But in the gist of it, is basically just hooking allocate virtual memory, write virtual memory, protect virtual memory, and create thread, which are the classic API calls that are being made for process injection, and which is also the API calls that my my loader is making in the backend. So my demo loader, the first iteration, if you have your GitHub repository open with demo loader, that one imports kernel32. And as I already mentioned, kernel32 will one level lower call the ntdll functions. So if I place my hooks onto the ntdll functions, which is the case here, it will by default also capture all the kernel32 hooks or even subsequent calls that would be called on a higher point of view. So what happens now if I would launch my EDR tool to inject the silent strike DLL, which is the DLL of my EDR, into the process? Well, you would see in process hacker that silent strike.dll is indeed loaded into my demo process. And if I hit the key to allocate memory, it will show me a message box. If I hit the key to write memory, it will show me a message box. And if I come to the point where I want to create a new thread and actually execute my shellcode, it will just kill my demo loader, and it will thus prevent the message box with evil payload from showing up. So if I would show you that live, I would need to open a new PowerShell window as administrator, so my EDR can actually inject its DLL into the demo. So I'm just going to start the listener. So here you can see that the silent strike injector is now waiting for my demo.exe process to be launched. So if I would now create a new process of my demo launcher, which I will do here. You will now see that the process has been spawned, the notepad has been spawned, and if you would look here, it's actually injected into my demo process, and I can verify if this is actually the case. So my EDR is helpfully giving me the process ID. So if I would search for 17716, I indeed get my demo. And if I would look here, indeed, Silent Strike DLL is injected into my demo loader. So if I would now close this up once again, go back to my demo loader. Which is here. I hit the key to allocate memory. You will see allocating memory detected. Right, detected. You want to allocate a new thread? Well, no, I'm not going to let you do that. I'm going to kill your process now. And if you would see here, if I press OK, boom, my process got killed. I now am back into my regular prompt, and no message box has been popped. So my payload got successfully prevented from launching. I hope that makes a bit of sense to everyone. Now, there's a quick win, which used to be quite effective, but EDR vendors quickly caught on, which is actually messing with creation flags. So there is a functionality in Windows to create process mitigation policies, and one of which is actually to block non-Microsoft binaries. So what that means is if you would launch a new process, no DLLs can be injected into your new process that are not Microsoft signed. So in practice, that would mean if an EDR or an antivirus solution does not have its DLL signed by Microsoft, it will not be able to inject itself into your process and thus be completely blind of what your process is trying to achieve. And if you would launch a process with this mitigation policy on there, you will see that there is a difference here, a subtle difference. So here you will see this is just the regular spawned demo process. So with mitigation policies, you just see DEP and ASLR enabled, which is default for modern Microsoft architectures. But if I spawn a process with this mitigation policies, you can see that there is now an additional mitigation policy called signatures restricted between brackets store only. So that's an indicator that I now have successfully created a process with this mitigation policy in place. And on top of that, I'm also doing parent ID spoofing. So here you can see that PowerShell.exe is my parent process to my demo launcher. That is because I spawn my demo from my PowerShell prompt. So that is indeed the expected parent. But if I mess around with the creation flags of the create process, I can actually specify an arbitrary process on the system as long as I'm able to open a handle to that process. So for example, if I would want to spoof LSAS, I can, if I am an administrator, because administrators only can open handles to LSAS. You cannot open a handle to LSAS without administrative privileges. However, Explorer.exe as a normal user is not a problem at all. So it's trivial here to just select a parent which you have access to from your current privilege level. So it could be Explorer, could be Internet Explorer, could be calculator, it could be anything really. So with these two things in mind, you can already see that it's getting harder for EDRs, antiviruses, and SOC analysts even to create the correlations, because now you effectively broke the parent-child relationship as you specified an arbitrary parent. So I created a bit of a malware protector demo. So this is the code in the GitHub under demo malware protector. So here you can see I'm spawning a protective process, but in order to do that, I have to leverage Win32 API calls, and I love C#, so I'm more of a C# developer. So I have to do some memory shenanigans here from unmanaged land to managed land, which is why you can see Marshall calls here to allocate memory into my managed codes and create pointers to that managed memory as well. So here I first create all the memory that I need to tamper with the security attributes and process information. So then I do the proc threat attribute list. Initialization, I want to manipulate 2 attributes. So one will be the mitigation policy and the other one will be the parent process. So first I have to initialize it like that, so it sees that I want to manipulate 2 of them. And then I have to initialize it once again to actually start being able to write to those initialized threat attribute lists. So here I'm writing the mitigation policy. As you can see here, I'm using the struct.binary signature policy block non-Microsoft binaries allow store. So that's the one that I showed you on the slide as well. And here I'm spoofing the parent. So I'm using the parent process flag to actually specify an arbitrary parent handle. And then I create my process with these flags. And because it's a demo application, so it's a console application, I have to specify that I'm creating a new console as well, and that extended startup info is present because I needed to manipulate the startup info. So I needed to have that extended startup info present. And it needs to be called like that in the create process flag. Otherwise, it will not take into account my newly created attributes. So if I would now launch my demo injector using my malware protector, so creating that dependency of the non-Microsoft store only and the arbitrary parent flag, you will see that my EDR is now not able to inject into my demo.exe, even though, which is interesting, even though it says here that it is doing the injection. So it seems to be all right. But if I open up Process Hacker, you'll see here, unable to query module information due to protection conflicts. So even Process Hacker is now not capable anymore of checking the loaded modules because Process Hacker is also not Microsoft signed. So that means that my demo loader now has free reign because the EDR cannot see my demo loader anymore and thus cannot hook the calls that are being made from that process, which will result in the evil payload message box popping up once again. Unfortunately, though, vendors caught on to this trick quickly, and this is shown here on a tweet from Sector 7. So here in this case, Falcon, which is CrowdStrike, has a DLL that is actually Microsoft signed. And I took a look into my demo box as well, which has a McAfee installed. And it turns out that some of the DLLs from McAfee also have this Microsoft signed intermediate certificate, but not all of them. So that's quite interesting. So this EPMPTHE.dll has it, but the ATP AMSI-Guard does not have it, which means that this ATP AMSI-Guard DLL would not be able to get injected anymore into my process. And I can show you what that looks like, again, with a small demo. So I'm going to recreate my listener of my EDR, my demo EDR. So once again, I'm listening for the demo.exe, but what I'm going to do now is I will open a new window of PowerShell and use my malware protector, specify Explorer as parent ID, and again, Notepad as the target. So if I spawn that, you will see that indeed the demo got started. A new console is indeed allocated. You will see that from the EDR's point of view, indeed, it says that it got injected. But if I would open Process Hacker to, what was the ID? 19704, demo.exe. Now I still have the possibility to check it, but if I would refresh it, it will not show it anymore. So you can see here that Silent Strike, nowhere to be found. And if I check the demo, indeed, my parent is now Explorer, and it does have the signature restricted store only. So if I would now hit my keys, it would pop up my message box, and no EDR prevention got triggered. So I will press OK. That will kill my Notepad once again. So I hope this still makes sense for everyone. It's a bit unfortunate that I cannot see like live comments because of the delay, but I'm just going to assume that that it's quite clear for everyone. If it's not, feel free to ask questions. I will address them at the end of the presentation.
Yeah, we already have quite a lot of questions in, so be prepared.
Right. So this is, up until this point, I've been using Invoke, which is the default way of calling underlying Win32 API calls from C#. But Invoke has some disadvantages, and here I'm quoting De Wover himself, which is the main developer of Invoke. So .NET provides a mechanism called Platform Invoke, commonly referred to as Invoke, that allows .NET applications to access data and APIs in unmanaged libraries, between brackets DLLs. By using Invoke, a C# developer may easily make calls to the standard Windows APIs. However, if you use Invoke to call, for example, kernel32 create remote thread, then your executables import address table will include a static reference to that function, telling everybody that it wants to perform the suspicious behavior of injecting code into a different process. In addition to this downside, there is another one. If the endpoint security product running on the target machine is monitoring for API calls, which is what I demonstrated with my demo EDR, then any calls made using Invoke may be detected by the product. This is a downside of Invoke. And this is why Invoke got, well, saw the light. And this is also why I love Invoke, because in contrary to Invoke is capable of dynamically importing API calls. So that means that you don't have to specify anymore with the between brackets kernel32.dll and then give the function prototype. You can now do it during execution time, which is quite nice. And that's only the beginning, because that will not evade any EDRs anymore, to be honest, that functionality. But what does make it interesting is that Invoke provides you the functionality to evade hooks using manual mapping, deception, and Syscalls. So you have three different methods. You have the manual mapping, you have the deception method, but the deception method is not something I will go into today because I will run out of time. However, I did cover it a bit in one of the blog posts over at the NVISO blog. And Syscalls, which is definitely something I will talk about at the end. And my favorite part of this is also that it has function prototypes for a lot of the API calls that are commonly used in offensive tradecraft. And well, I'm a bit lazy, so I don't want to constantly go on the internet, search for the prototype, then port it into C#, even though it's quite trivial to do, because you have websites like pinvoke.net, which will give you the C# implementation of a certain API call, but it uses a lot of copy pasting work. I'm a bit lazy, so I just like to have the invoke there, where I can just specify I want to use this call, and it's already created for me. I don't have to do anything. So that's quite interesting. So the invoke, a bit of a primer. So it has a NuGet package. If you're not familiar with NuGet, it's basically a packet manager for C#. So you can import libraries from NuGet packages. That's what they call it, just like you would have NPM packages. However, the dinvoke NuGet package now is flagged by Defender. So, well, yeah, it makes it a bit less workable because it's already by default flagged by Defender. So no matter what you do, your code will be malicious because you have the dependency on the dinvoke NuGet. But you can also just download the source code on GitHub and import that into your code. And if you use that, so then you're not using the pre-compiled DLL of the NuGet, and that is not getting flagged as of yet by Defender. That doesn't mean that it cannot change, but it is not detected for now. And excuse me, I'm going to have a sip of water because I'm getting a very dry throat right now, so bear with me. So dinvoke is capable of resolving API calls in 3 ways. So you have the standard dynamic API resolution or resolving, which is a bit like pinvoke. It's not really intended to evade detection. However, it does get rid of the import address table calls. So it's quite cool, but it doesn't really help you in any way to defeat EDRs, for example. It does have manual mapping, which is something I will talk about. And it does have overload mapping as well. And overload mapping would be the functionality that you use for the deception part of dinvoke, but that's out of scope of this talk right now. And it has also a built-in injection API for process injection. However, it's not complete yet. It's still quite heavily under development. I'm trying to contribute as well in my spare time, but I don't really have that much spare time, unfortunately, which is also part of the reason why I'm giving this brown bag. It's to inspire some of the tool creators out here, should they be listening, to actively contribute to dinvoke, because we could really use the help, and it could make life a lot easier for offensive C# development. So with that being said, let's dive into manual mapping for the people that are not familiar with the concept. So as I already explained, when an EDR is present, it will typically hook certain functions in the loaded DLLs. Noteworthy will most likely be the ntdll.dll exported functions, such as ntallocate virtual memory X, for example. It's just an example call. And this is how regular mapping looks like. So this is not manual mapping yet. This is just to show you the flow of how it would normally work. So you would have malware. Malware is trying to call an exported function of, for example, ntdll. Say my malware wants to call ntallocate virtual memory X. Well, turns out they have an EDR in place. That EDR is also hooking ntallocate virtual memory X. So what happens now is my malicious payload, my malicious software, will call the hooked function. So the EDR solution will see that it's being called, it will inspect the call, it will see that it's doing something fishy, and it will trigger an alert. That's how it works in a nutshell. Obviously, it's a bit more complex than that, but just to make this as understandable for everyone, no matter how in-depth your technical expertise is, I just wanted to show it like this because it should be understandable to, I think, most people. So that is the normal behavior. Now, let's take a look at how manual mapping works. So manual mapping, instead of using the already built-in ntdll, so as I mentioned before in the beginning of the slides, every single process, I think almost every single process, maybe there are some exceptions, but I haven't encountered them. So I'm just going to say every single process is importing ntdll.dll into its virtual address space, because that's the bridge between userland and codeland. It needs that to function properly. So that is by default imported in there. What manual mapping does is it will not only import that by default ntdll.tll that gets hooked by the EDR, it will, in addition to that, import ntdll.tll once again into virtual address space. And it will then use the manually imported ntdll.tll to do the function calls. So what that means in practice is your EDR will be listening for nt-allocate virtual memory X at the memory base of the ntdll.tll, but you will be using another version of ntdll.tll, which is living at the same virtual address space, but at another memory base location of the normal ntdll.tll, which means that the EDR will not be hooking that one, which means that you can now call the NT functions without having to be afraid of hooks. And you can see that in this example. So here I created my EDR evader, which is using the Invoke. And here I'm using the manual mapping mechanism. So that's the -mm stands for manual map. So here you can see that I'm spawning Notepad with parent process explorer, process ID 6608, which is irrelevant. And then here you can see, please check the memory of this process in Process Hacker under this address to find the manually mapped ntdll.tll. So if we start taking a look at that, here you can see this is the manually mapped ntdll.tll. And if you would check what it looks like in Process Hacker, the base image of ntdll.tll is living at this address space. So this is the base ntdll.tll, so the real one, so to speak. And if you would compare the two, you will see that they are exactly the same. And if you can't tell the difference, the program can't tell the difference either. So the Invokes makes this very easy for you, because if you would want to do this manually, completely manually, so without relying on the Invoke, you would have to take care of all the exported functions of ntdll.tll, and you would have to manually start calculating the offsets, which is annoying to do. So the Invoke takes care of that for you. It's all automatically doing it for you. So by calling the mapped dll.module base, it actually already has the base address for you, and it does the calculations of the offsets for the exported functions for you as well. And what happens is that now the EDR will start checking EDR goes brr, which is the EDR evader loader that I made. It will still inject its silent strike DLL, so it will act like a normal EDR would. It will still inject itself into it, but it will be blind, because it will be hooking the ntdll calls, but not the manually mapped ntdll calls, which will result in me having the capability of still bypassing my ghetto demo EDR and spawn the evil payload. So if we would demo this, I'm going to start from a clean slate once again. So administrator prompt, start the listener of my EDR. Yeah, that's not right. Needs to check. I think it's with 3 R's. Yeah, it's with 3 R's. All right. So it's checking for EDR goes brr.exe. Then I will spawn EDR goes brr.exe with the manual mapping method. Oh. So EDR goes brr, parent will be Explorer, spawn process will be Notepad. I'm using the manually mapping method. So I'm going to launch that. You'll see that indeed the Notepad gets spawned. You'll see that EDR goes brr does get injected with silent strike. I will check if that's indeed true. So if my EDR is not lying to me. So 15912. Let's check the modules. Yeah, silent strike is indeed loaded into my process. Yep. Let's hit the alloc. You see, no message box. Right, no message box. Injecting. Up. It will spawn the message box once again. I click OK. The notepad disappears and my EDR got bypassed once again. So that's the manual mopping method. Then we will talk about syscalls. So as I already mentioned in previous slides, what syscalling basically does, it will just copy the function prototype of an ntdll exported function, and we will create our own function for it and point our code to our newly created function, which will be an exact copy of the nt function. But it will not be hooked because, well, it's a newly defined function. It's not an exported function of ntdll.dll. So the EDR will be blind and the syscall will launch and everything will be perfectly fine for the EDR while the malicious payload will get executed. So not much to see here. Once again, silent strike is loaded, but the message box will pop up. And if we do that right now, so just admin, there you go. So what I'm going to do now is once again start my EDR goes brr executable, but now I specify SC, which stands for system calls. So not the manual mapping method, but the system call method. So I launch that. Once again, the notepad pops up. Once again, my EDR says, whoa, look at that. Nice. It's a very clean process ID. So if I would check that process ID, like that, but like this. Once again, silent strike is in there. So everything works dandy. Alloc, write, shellcode, and once again, evil payload gets executed, completely evading my EDR. So that's pretty amazing timing, if I say so myself, because I'm actually at the end of my my presentation. So the closing note here that I want to give is the Invoke needs your help. It's still quite new. It's still under active development. Not a lot of the function prototypes of all API calls are in there yet. I've contributed quite a bit myself. I know that Rastamaus, if he's still listening, because he told me that he would join the call as well, also contributed a bit to this project. And of course, the Wover himself does the heavy lifting for us. But we could still use some active contributors. So if you just have some free time and want to port over some C++ function prototypes from the Microsoft documentation into their C# delegate equivalent, please feel free to do so. Please submit those pull requests. We appreciate it a lot. And with that being said, I thank you all for your attention. I hope that this was an interesting brown bag. I had quite some fun myself creating it. I spent quite a bit of time also writing the code and stuff like this, so I hope it's appreciated by all of you. And yeah, I know that Robin told me already that there are a lot of questions, so without further ado, let's just tackle them. Huh?
Yeah, all right. Thank you, Jean. So let's go through the questions. This session was originally planned till 1. I don't think we will be able to put all the questions in the 2 or 3 remaining minutes, but if it's okay for you, Jean, I just propose we go a bit over time and answer them all. But if any of the people here in call need to leave at 1, as I mentioned in the beginning, this session is recorded. You can view the recording just by going to the URL you originally used to join. So we will handle all the questions right now. If you have to leave, you can watch them afterwards. If you have any additional questions, you can reach out to us on LinkedIn and Twitter at NVISO Security. So yeah, let's go to the questions now.
Yes. So what is your favorite way of exfiltrating information while being stealthy from a host if there are EDRs in place? How would you do post-exploitation on systems with EDRs in place? Do you have any favorite ways of establishing persistence against EDRs? So let's tackle that one by one. What's your favorite way of exfiltrating information? Well, normally in red team operations, you will use a command and control framework. Any decent command and control framework has exfiltrating capabilities as well. So what I do is just exfiltrating over the command and control. Usually what I did in the past was I domain fronted quite a bit. So I was using legitimate traffic, for example, ajax.microsoft.com, and just exfiltrate in chunks. So with jitter, data size differentiators, and differencing in size and timing. So that's a bit of the stealthy way of how to exfiltrate data, in my opinion. So that would be an answer to your first question, I guess. Now that domain fronting is dead, well, it's not completely dead, but it's going to be killed. I would suggest using tools like C3 or is it C4 to actually use legitimate software as a service services such as Dropbox or Google Drive to actually proxy your command and control traffic over those vendors and use those to start exfiltrating the same way as you would normally do. So how would you do post-exploitation on systems with EDRs in place? Well, that's kind of basically the entire point of this presentation. So it's basically using Syscalls. Do you have any favorite way of establishing persistence against EDRs? Yes, I do. I use COM object hijacking quite a lot. It's my favorite way of establishing persistence because, well, it's rather stealthy as there are literally thousands of COM fires every single minute on your workstation. So it's quite hard to monitor those. That's why it's one of my favorite persistence techniques. How does this EDR differentiate between legitimate and non-legitimate syscalls? I have no idea what you mean by that question. It's basically just hooking ntdll.tll. So it's not differentiating any syscalls. You evade this demo EDR by just using syscalls, because if you use syscalls, as I already mentioned, you're essentially just making a copy of the exported function of ntdll, but you're not hooking. Your EDR is not hooking at that specific function. So if that function isn't hooked, there's no logic behind it, and it's evading your EDR by default. So I hope that answers your question somewhat. Would hooking syscalls be the ultimate protection against user mode evasion attempts? Yes, I guess yes. It would, but I think that's probably going to give you a lot of false positives. I see that you linked a GitHub repository there, but I haven't taken a look at that repo yet. So I don't know. I might get back to you on that one. But in my opinion, if you find a way to start hooking syscalls, yeah, that's a very decent user mode protection. Of course, that would still mean that if an attacker would have kernel level privileges, it would still be able to bypass it. But yeah, that would be a nice start if the syscall hook works. ID, in your demo process, you enumerate all threads of your process and you identify the threads of the injected EDR DLL and then suspend these threads. What do you think? Yeah. Yeah, Didier, yes, that would be an interesting idea. I haven't tried that yet. Yeah, that would work as well if you would do it like that, I guess. Yeah, but you just have to figure out a way on how to do that, because now I'm just thinking out loud, but maybe the EDR threats are also needed for your program's legitimate behavior. So if you would suspend them, you might start getting wonky behavior. I don't know. I would have to look into it, to be honest, Didier. I don't know. Maybe you're right, maybe you're not. Is the parent-child process spoofing a flag for EDRs? Well, it depends on your EDR. Some EDRs flag on it, some don't. So it's entirely vendor dependent. How do you deal with EDR against Linux or MacBooks? Well, that's a completely different topic. This one is just using Windows as an example. If you want how to deal with EDRs against Linux or MacBooks, maybe that's an idea for another brown bag. But talking about that will probably set us back another hour. So I will not divulge into that right now. How do userland hooking work if you're how does userland hooking work if you are just a standard user when EDR needs to be kernel driver, which has more privileges? I have no idea. Sorry, but your question doesn't really make a lot of sense, because yes, your EDR needs kernel drivers, but it's just hooking userland. Obviously, it's not just doing that. There are kernel callbacks on there as well, but that's not the scope of this brown bag. So I'm not quite sure how to answer that question, to be honest.
There was an answer by Restamouse, but I'm not entirely sure whether it was an answer to this question.
You're in a process, you have relative free reign to manipulate it. Well, yeah, it does kind of make sense, I guess. Indeed, Restamouse makes sense. So you own the process, you created the process, you spawned the process. So yeah, you have full access to that process's virtual address space, which means that you can, in that specific constraint of your process's address space, you can do whatever the hell you want. So the Invoke source code uses Win32 calls with dynamic API Invoke, which does not bypass userland hooking as far as I know. Yes, that's exactly what I said. For example, the manual map module from disk uses Win32 API calls with dynamic API Invokes. When the Invoke source code get blocked by EDR first before our code's written in the Invoke can run? Well, no. From my experience, no. It could be, well, your mileage may vary, of course, right? I haven't encountered all the EDRs in existence on the universe, on the planet, during my red team ops, but most EDRs that I've encountered, well, okay, slight caveat, I'm not using the source code, open sourced, the Invoke, like you see it just on GitHub, because, well, indeed, it's open source. That means that EDR vendors can start writing signatures for that. I did some minor modifications to a private EDR, to a private Invoke branch that I have, and I'm using that in operations. So no, but essentially I didn't change the flow, so it's still using the Win API calls. So no, in my experience, the EDR does not block the Invokes API calls, because in general, the API calls that are being made, and I'm just going on a limb here, I haven't taken a real good look under the hood yet, but I would assume that it's using get proc address at some point, and EDRs typically don't hook get proc address. There is a pretty good GitHub repository from Mr. Unicoder, which attempts to map all the hooked NT functions from all the EDR vendors out there. And like get proc address, for example, is not one of the API calls that I see being regularly hooked. So what I commonly see in EDRs is they specifically hook all the API calls that can potentially be used for malicious purposes, and not as much as like trying to hook the entire exported function tree of ntdll.tll, because that would just create a lot more overhead. It would make all the processes slower, because it would make the logic a lot longer, right? If you place hooks everywhere, then it's just going to take a longer time. And well, so some businesses, it really depends, but some businesses do have that requirement to keep their applications running as fast as possible. I'm going on a limb here and talking about stock markets, for example. I imagine that every millisecond there costs money. So you want to make your EDR as performant as possible, which is why you don't hook every single function. And that's basically why the Invoke underlying API calls to do all the resolving dynamically are not being blocked as of now by EDRs. Was the window defender turned off when you were running these demo apps, or were you just focusing on silent strike bypass? I was just focusing on this demo EDR for this purpose. I am not going to kick any EDR vendor in the groin by bypassing their EDR solution here live in a brandback session, because that would be very uncool. So that's why I created the demo EDR just as a proof of concept, but rest assured, if you use the concepts that I explained here in this brandback, you should be able to bypass any major EDR vendors out there. How often do you see EDR solutions with combination of userland hooks, kernel driver callback, and ETW in real-world engagements? I feel like even if you bypass userland hooks, kernel callback can be used to stop payloads. Yes. Yes. How often do you see it? I see it all the time. In regular engagements, you will not only rely on Syscalls, you will also try to get a malicious driver on there, for example, using the KDU project in GitHub to get that kernel level read-write privileges and disabling or potentially even poisoning the kernel callbacks from your EDR solution. And ETW can definitely be bypassed. For example, you could just patch it in memory, or you could use ghost in the logs from botsec. There are a ton of possible ways to bypass or to mute ETW. So in real life engagements, you would have to rely on a combination of both Syscalls, ETW bypasses, and kernel level callback stops. Or another way around this would be to just heavily obfuscate your payloads, so you don't have to rely on any of those, and your payload just runs off the shelf without having to try any evasion tricks. If you obfuscate enough, you should be able to bypass EDRs as well without having to even rely on Syscalls. Voila, I think that's it, unless there are any other questions that I haven't seen yet, but yeah, I guess that's it.
No, indeed, that concludes the Q&A section of the presentation. I want to thank you once again, Jean-François, for doing this presentation. Thanks a lot. I also want to thank everyone who joined today. We organize these kinds of sessions on various cybersecurity topics almost every Thursday. Next week, we'll host Didier Stevens, which will present his various open source tools which he developed. So I hope to see some of you again next week or one of the weeks after that. So these NVISO Brownback sessions are organized by NVISO. We are a European cybersecurity firm. We offer a wide range of security services. So if that's something that interests you, you can find more information on our website, nviso.eu. And we're also hiring, so if that's something that interests you, you can visit nviso.eu/jobs. So that concludes the presentation. Yeah, once again, thanks everyone, and take care.